Welcome to From Zero to Zeta, where we will be discussing various aspects of mathematics, beginning with how mathematicians think. First off, this is my first video ever, From Zero to Zeta, Episode 1. I'll be watching the comments for feedback, and make sure to hit that subscribe button if you want to hear more. A little bit about me. I have a master's degree in mathematics. I live in the San Francisco Bay Area, and I have a passion for math. I wanted to make some videos sharing that with you all. Today, what we're going to talk about, since it's a very first episode, I wanted a topic that would make sense to everyone. We're going to be exploring how mathematicians think. Every once in a while, you hear about one of those proofs that they solve, and you may read through some of them and think, how did they come up with this? Like, there's no way I could ever do this. Well, I'm here to change that. By the end, I'm hoping you get a little bit of understanding in how we tend to think about these sorts of problems. First thing I want to show you related to this is the 15 puzzle. All right. So many of you may have seen this before. It's this typical sliding tile puzzle where you have to order them from 1 to 15, and it's a 4x4 grid. Now you may be wondering, what does this have to do with math? Like those numbers could be anything. They could be pictures, right? We'll get to that. First, I want to just explore this puzzle a little bit. What can we do? We can move up, left, right, down. We can do this at any point, right? Except for the edges where some of our directions aren't available. Like on the edge here, we can't move left. And by moving, I'm talking about the empty space, right? If you just follow the empty space is moving left now. Now it's moving right. But the actual tile is moving the other direction. But the empty space is our point of reference. That's where we are in the grid. So that's what I will be referring to. Now, the goal is to get 1 to 15 in order. That means we need 1 up there. We do something like this. And we have 1 in the correct spot. We want 2. And 2 is now in the correct spot. All right. And 3. And so on, right? So you'll notice that they turn orange when they're in the correct spot. What can we actually do with this? Instead of looking at it like a game, let's take a look at the rules. We obviously can't move tiles willy-nilly. We can't like switch 15 and 10, for example. The rules are we can move in any 4 of the cardinal directions. What's going on here? It feels like there's some kind of structure to it, because there's a set of rules we have to follow. Let's move over to the, actually, we'll do this. Notice if we number it from 1 to 15, and this is our current board state. Okay, so this is our current board state. What can we do with this? We can move, if we move left, so that's that's moving our empty space left, right? So that means we're moving the 10 right. So our board state looks like this. And we can also move down and up. So if we move up, that means we're moving the 3 down. So our board state looks like and we can also move it down. And then we can use these same rules on each of these states. We can, if we wanted to take the down state here and then go back, we moved from there to there, we moved from there to there, we moved from there to there. Now here's a question. Can I undo any move? If I take the down state, for example, put the 4 back where it was? Yeah, absolutely. This allows us to undo any possible move, right? We have this undoing power. We have this reversibility with moves. We can undo any move, and each of these number positions we call a state or configuration. And the moves allow us to go from one state to another. In math, we call these operators, right? They allow us to go from one state to another. And something you may not think about explicitly is that order matters, right? We can't doing the same thing if we go up and left, for example. That doesn't give us the same board state as going left and then up. Another thing with the 15 puzzle, often used sequence, is square rotation, or rather up, left, down. And what that does is it rotates the square so that you can then come over to the other side and do the same thing there. And now the 2 is in the corner. For convenience, we often think of this as a single move, a single pattern, right? In a Rubik's Cube, we have a certain pattern that we follow for seeing a certain effect. We think of that as one thing. We often think about a sequence of moves being a single move. And what we call that is composition. We're composing moves with each other to allow us to access a board state further down the line. In this way, all possible board states are connected by a series of moves. We have an identity, which is something that does nothing to the state. In other words, we can make no move at all, and it will not change the state. And we can consider that a move, just like we considered the composition of moves a move, because we can move down and then back up. That is our undoing. So if we look at the identity move, or rather no move, we can look at it actually as a composition of moves, which we have stated before can be thought of as a single move. We also have the power of undoing, which in math we call an inverse. So moving down is the inverse of moving up immediately. Now, we have to be careful, because if we throw something in the middle, like if we move down, left, and then up, it's not undoing the first down, right? So inverses only apply if they happen in sequence. So if we move down and then up, or up then down. There are longer sequences as well that can add up to an inverse, however. For instance, going back to the rotation of the square idea, we can move left, then up, then right, then down. and then left, and then up, and right, and down. And if we do this enough times, we get back to where we started. There are other ways to get back to the identity, in other words, not changing the state, through series of moves than just inversing immediate. But we don't necessarily know how those work in the long run, especially as these structures get larger and larger. One thing that will always get you back to the identity, no move, is doing a move and then immediately undoing it. You throw anything in the middle and it's no longer that pattern. And then another thing we can do is we can compose these moves. We can make a sequence of moves at once, right? So left, down, then right, that is a composed move. We're chaining these moves. We call that composition of moves. Later, you'll see that these moves are actually functions, but we're not there yet. This is the kind of system mathematicians like to study, because this game is made of rules, right? You can completely replicate this game by specifying exactly what the rules are and how to set it up. All right, so we got a 4x4 grid. We can move. We have exactly one empty tile. The rest are numbers. The goal is to get all of the numbers in order, and the only ways we can move are up, left, down, and right from the empty tile. We can move tiles by sliding them, but we cannot pick them up. We're getting into the heart of what mathematics is all about. Mathematics is about rules. It's not even really about numbers. It's everything about how they interact and how structures interact. Numbers form a structure with addition and subtraction, right? So we get 1 plus 1 equals 2. So what we're doing there is we're adding 1 to 1. We're interacting those two objects to get another object. This is how mathematicians form abstracted ideas. They list the rules, and maybe they say, oh, hey, what if this rule doesn't apply? Well, that's a generalization. What if we made the 15 puzzle, but we couldn't move down? Then the rules are, well, we couldn't necessarily move down. That's why it's a generalization, because then what we have is a system where we can move up, left, and right, but now we're throwing in all of the puzzles in there where we can't move down. But the puzzle where we can move down is still in there. So it's a sort of step back, a broader picture. Now we're dealing with the 15 puzzle in this case as a system rather than just solving it. We're looking at this puzzle as a system. What other systems work like this? It seems like what we described, doing nothing, the ability to do nothing, the ability to undo whatever you just did, and doing something in sequence. It feels like those are pretty universal things that you can do to a system. Like, you can't necessarily undo any particular thing. For instance, if you square something, you can't you can't undo it per se, because you get two possibilities. There are systems in which undoing doesn't work. You can't undo something. There are systems in which the identity doesn't exist. Like, there is no do nothing. These sorts of structures, that's what we're looking at when we're abstracting this. We're no longer just looking at a 15 puzzle. We're looking at how it works and why it works the way it does. What do we need for this to work? Well, we need a set of values. We need a um, set of values okay. Now, what do I mean by a set and what do I mean by values? When I ask you the value of something, you probably think, how much money is it worth, right? That's how much value it has. But that's not what I mean by value in this case. A value can be anything. It's just a an entry in the set, and the set can be made of whatever, right? So a set could be a set of numbers, it could be a set of basketballs, it could be a set of cars, it could be a set of intangible things. We can literally put anything in a set, so anything can be a value in that set. We do need a set to work on. We need a way for these values to interact, some way to combine them or transform them. We'll call this an operation on this set. And what do I mean by an operation? Well, exactly what we're talking about with the moves on the 15 puzzle, right? We can make a move, we can and that is the same thing as applying an operation. And then we need an identity value. Something that when we apply this operation with it to another value, it doesn't change. So it keeps all other values constant. Okay. So what can we think of that behaves like this? Well, we have integer addition, right? So we can uh, our set is uh, the integers. So from 0, 0, 1, 2, 3 to infinity, and -1, -2, -3 to negative infinity, right? So and what's our operating? What's our operation? What is changing values as we apply it? Well, our operation, that's addition. And our identity, what's our do nothing value in this set? Well, that's 0, because 0 plus anything is that same thing, right? So that's what it means to be an identity. Um, and we need composition. This is part of what makes it an operation, All right. So what's our composition here? Well, we can keep adding to the result. So 0 plus a, well, that's a, and then we could add 5 to it, and then we could add -2 to that. All right? And so each one of these is applying the operation. Each one. So when we're doing it in sequence like this, that is a composition of that is a composition. What we described with the 15 puzzle, we'll go back to that here in a second. So what we the structure that we just outlined applies here as well. Our identity is making no moves. Our operation is moving left, up, down, or right. And our set of values is the set of board states possible in the 15 puzzle. So you'll note here that the values are no longer numbers, right? They're board states. The board states have numbers in them, to be sure, but the values themselves aren't numerical. So, and then we can compose these by moving from board state to board state several times in a row. So we have composition. There's a structure in mathematics that exactly captures this kind of behavior. It's called a group. We won't dive into it very much. I'm not going to share the definition yet today, but it shows up again and again, and it's because it is literally defined by these rules we just outlined. We're not doing anything crazy by saying, "Hey, what's going on in this very specific circumstance?" In fact, we're trying to boil it down to just the necessities. Like, how can we abstract this, generalize this as much as possible, so that we just figure out, so that we can apply the same logic to many different things. For instance, Rubik's Cube has the same thing. You can rotate it, and then you can rotate it back. So that is inverses. So we have inverses. And we have composition because we can keep doing things to the Rubik's Cube and it stays a Rubik's Cube, right? No matter what we do. What are our set of values? The set of values is the set of, actually, here, we'll do that. Set of values is all of the possible states of a Rubik's Cube. And our operation is moving one side in either direction. So the same structure, the same set of rules applies here as well. A lot of systems have this structure, this group structure. One thing mathematicians really love to do for any given system is something called axiomatization. Axiomatization. And what that means is it's the process of writing down rules for a given system and exploring it that way. And that process can often result in some interesting abstractions too. Let's talk a little bit about that. For the 15 puzzle, we'll look at this one. Do we axiomatize it? Axiomatize it. So we want to describe the system completely. All right. So first, what's one thing we notice about the board size? All right. Well, it's a 4x4 grid. Okay. And then we have exactly one empty tile, empty space. We don't necessarily have a goal in mind for the puzzle, so we don't need to write down the goal as an axiom, because we're just looking at this puzzle as a system to study rather than any particular goal in mind. So we're not going to write down the goal in the axiomatization of it, but we do write down how we move from one state to another. So we can move left, right, down, or up. Okay, so that is the axiomatization of the 15 puzzle. Now, where the abstraction comes in is by removing some of these rules. So, for instance, what if we remove the first rule? If we remove the first rule, then our board doesn't necessarily look like a 4x4 grid anymore. All right, so we could have a board of 4x5. Or I guess 5x4. Right, and then maybe this spot is the empty one. Right, that's the empty. And then our goal would be to go from 1 to 19 instead of 1 to 15. Or we could have a grid that looks like this. 5. Now, it's these configurations that tell us that by removing this rule, we don't always have something that can be solved. So we'll call that the empty square. We can only move it up and down, right? So the order, let's say this is like 1, 3, 2, 4. We can never swap 2 and 3 the way we want them to be, because we don't have any lateral movement capability. So by changing the board state, or changing the board dimensions, we can actually change whether it's solvable or not. And then, well, what if there is not exactly one empty space? Well, that means there could be less or more. If there are less, we'll go back to the 4x4 just to edit one rule at a time. Uh, there we go. So now we're just removing rule 2. All right. So we go back to the 4x4. And we could have 0 empty space, which means there's no room at all to move anything. We can't move anything. If there are 0 empty spaces, there's nothing to move, right? We can't move left, right, down, or up. So by default, almost, that is unsolvable unless it's already solved. Like, unless it's 1 to 16 in a row, and it's already solved, it can't be solved. And in this case, the identity move, the one where we don't move anything, that's, in fact, the only thing we can do. The only thing we can do is nothing. If we go the other direction, we can abstract this to more than one empty space. So maybe it's that one and that one. Right? Then it actually becomes a bit easier. Because that gives us more space to move around. So we can now move this square up, this empty spot up, left, right, or down. And we can do the same thing with the other one. So both of these options allow us to generalize this kind of puzzle. It's no longer a 15 puzzle at that point. This would be a 14 puzzle. But also a 3x5 with one empty square. That would be a different 14 puzzle. So now without rule 2, we have suddenly the number referring to the puzzle is no longer unique, because these two different 14 puzzles are different from each other because they don't have the same dimension, they don't have the same number of empty spaces, etc. So they're going to have different solutions. So this is what I mean by we see some interesting abstractions that we can make if we don't have rule 1 or 2. All right. Now we could unpack this one to actually 4 separate axioms. Let's call this 3A. We can move left. 3B. We can move right. 3C. we can move down. And 3D, we can move up. And so removing some of these also generalizes our puzzle. Although I would argue not in a good way, not in an interesting way, because it generally makes the puzzle unsolvable by removing one of those. The interesting ones to remove are the 4x4 grid and the exactly one empty space. That is what changes the puzzle in the most interesting way while still allowing the possibility for solutions. Next time, we will take a closer look at examples of this. So how do we axiomatize the integers under addition, for example? Or how do we axiomatize the Rubik's Cube? Because that way of thinking, that is really the core of how mathematicians think. If we can come up with a set of rules for it, then we can reason from them. And that is what most of the higher maths are asking you to do, requiring you to do. If you want to hear more of this, go ahead and click the subscribe button down below. Again, I'll be watching the comments. I know it's not always a good idea to watch those, but I'll be watching them for the next couple weeks for feedback. Yeah, I will see you next time.